anything we want with it. So within our fake payment processor, we don't actually process any credit cards, but we do have a couple of fields that we want to be able to access. One of them called was called, one of them called amount passed, and using these we're able to verify that this method was called and that the amount passed is the one that we expected. If we were interested in verifying the payment details, we could expose those here as well, and then check for them in our test. Remember that the point of unit tests is not to verify that the full system works, or to test whether or not the payment processor itself works. The point of the unit test on order.checkout, which is the method that we're testing, is to verify that checkout does what we expect it to do. What do we expect checkout to do in this case? Well, we want it to process a credit card with the correct amount. We want it to call our reservation service. We want to call our notification service. We want to know that it does these things, and perhaps that it does them under certain conditions and in a certain order, if necessary. And that's it. We don't want to have to test every little piece of the system just to test this one method. And that's what separating out the dependencies is allowing us to do, is to isolate the order.checkout method and be able to test just the content of this method without having to have actual implementations of all of its dependencies. If we look back at one of the original methods, tests that we had, a test here that said that it should not fail with no items, no credit card, but it should have notification. And if we run this, we see that we get this exact same behavior that we did before. Now let's look at the class dependencies on online order and compare them with what we had with order. We've broken away from having dependencies on many of the concrete classes that order had and replaced those with interfaces. So we now have dependencies on 3 interfaces: reservation, payment, and notification, as well as dependencies on still payment details, the cart, and the order. But those we're able to new up without any kind of external infrastructure requirements like web services, database, SMTP, servers, etc. And so this still allows us to test our online order without having to use any of those extraneous bits of infrastructure. So just to review, the main change that we made is we went into online order, we identified the dependencies that it had, and created interfaces for those dependencies. We modeled those interfaces based on simply what this particular class needs. So the client is the one that dictated what these interfaces should be. And then we moved the implementation details that previously existed in this class into implementation of those interfaces. And this was pretty much just a straight cut and paste of method that we had previously on order. We moved into now notification service, who currently has just one responsibility of sending this message to a customer. This makes this particular class very easy to test and very easy to follow because it's doing only one thing, and it cleans up our online order class considerably as well, so it's much easier to follow and simpler too. The nice thing about this is that online order is now being very explicit about its dependencies. You know when you create an online order that you must have a cart, a payment details, a payment processor, a reservation service, and a notification service. If you don't have those things, you simply cannot create an online order. There's no default constructor for it. And so we are able to tell clients of the online order class exactly what dependencies it needs in order to function. Now let's take a look at some design smells related to the dependency inversion principle. The first one is the simplest. It's simple use of the new keyword. If you find in your code that you're using the new keyword and moving up actual instantiations of particular instances of classes rather than interfaces, it's often a sign that you could apply dependency inversion principle. In this case, what we're showing you is this new inventory system. This is something that if it has external dependencies, maybe it's talking to a database, now the code around it has inherited that dependency. So the only way for you to keep this for each loop from having to deal with whatever the dependencies that inventory system carries along with it is to replace that with abstraction. And the simplest way to do so is to replace it with an interface that you use and then simply inject that interface using the strategy pattern and constructor injection. Similar to the use of the new keyword is the use of static methods or properties. This can be something as simple as a datetime.now that's crept into your code. Instead of having an actual datetime passed in, or an abstraction such as an iCalendar or an iDatetime interface that supports the now method that you want to be able to pass in. Another very common scenario is the use of static methods to create sort of a facade layer for your data access. And so you'll see this frequently where you have something that offers a bunch of different methods like save customer or validate customer or things like that, which are static. And unfortunately, if you have a method that does a bunch of stuff and then ends with data access.save customer, and that static method talks directly to ADO.net and talks directly to the database, there's now no way to eliminate that dependency on the database. Just the same if that static method is talking to a file system or any other dependency. So the best thing is to avoid static methods because of the fact that they cause these kinds of problems with inherited dependencies. The one place where you should use or could use static methods is when they don't actually touch anything other than the parameters that are passed into them. For example, if you had a static method that added two numbers together and it took in those numbers as parameters, there would be no problem with that because it's not going to cause any sort of dependency problem. But if you have a static method that instantiates other classes, and those classes might have dependencies of their own, now that's something that is going to likely cause you problems when it comes time to test. If we're not instantiating our objects, where do we instantiate them? Somewhere we have to do this. So typically what happens when you apply dependency injection is you get many small interfaces, which is good because each one of them is very cohesive, they're loosely coupled to one another, they follow the single responsibility principle, they follow the interface segregation principle, but at some point you have to actually create these objects. There's a couple of different choices for this. The first one is you can create a default constructor that then inherits from your constructor that actually takes in the interfaces and provides a default implementation of each of those interfaces. So in the example that we showed, we had an online order that took an iNotification service as one of the parameters in the constructor. We could create a default constructor that automatically passes in a new notification service, which is our default implementation of the iNotification service. Now any code that is calling this will continue to work just as it did before, and we'll still be able to inject alternate implementations, for instance in our tests, when we wish to do so. This is sometimes called poor man's dependency injection or poor man's IOC. IOC means inversion of control, and we'll see that in just a moment. The other option is to manually instantiate everything in your application start routine or main method. In a web app, this could be an application start in the global ASAX. And another option is to use an IOC container, which does the same thing, typically in the main or startup method, but it has a bunch of features that it supports so that you can wire these things up in an intelligent fashion and go one place and see how your object graph is going to be set up for your application. So IOC containers, or inversion of control containers, are responsible for object graph instantiation. They're initiated when the application begins, and typically they either use code or configuration, such as an XML file, to determine what is going to be set up to be used whenever an interface is called for. Managed interfaces and implementations to be used are registered with the container. So for instance, you might have in your container something that says you want to register iNotification service and say that anywhere I see an object that requires an iNotification service, I want to use a new instance of notification service. Dependencies on these interfaces are then resolved either in application startup or at runtime. You can call an IOC resolve method that will go and find whatever the instance is that's mapped to that interface at runtime. Or you can have a container that automatically is able to create the dependency graph for a given class by using its constructor. Typically, the constructor that has the most parameters is the one that we'll use. So in the example with our online order, we could have an IOC container create one of those for us, and it would automatically supply the types that were needed for the iPayment processor, the iReservation service, and the iNotification service. Sometimes it's necessary to create a factory class that is able to create your class for you and then register the factory class and its dependencies with your IOC container. IOC containers are a fairly large topic in and of themselves. There are quite a few of them available, most of which are completely free. Some of those are listed here, including Microsoft Community, Structure Map, Inject, Windsor, and Funk or Monk, just to name a few. So to summarize, you should depend on abstractions rather than concrete types whenever possible. You want to avoid forcing high-level modules to depend on low-level modules through direct instantiation or through static method or property calls. You want to declare your class dependencies explicitly in their constructors wherever possible. You can inject dependencies through such constructors, or alternatively through the property or through a parameter injection. So the fundamentals that are related to this topic include SRP, ISP with a side pattern, and inversion of control containers, as well as the strategy pattern that we discussed. I recommend the Agile Principles, Patterns, and Practices book listed here, as well as Martin Fowler's article on dependency injection, which is at the URL shown right here. I need to provide credits for the one motivation picture I used for the dependency inversion principle, as shown here. And with that, thank you very much. This has been part one of a Principles of Object-Oriented Design Software Fundamentals, the Dependency Inversion Principle. We're going to have another second part to this that's going to show you how you can apply this principle at the application level and at the solution and project level in your Visual Studio projects. Thanks. Hi, this is Steve Smith, and this is going to be part two of the dependency inversion principle, one of the principles of object-oriented design and a software fundamental, part of the solid principles of object-oriented programming. In this module, we're going to talk about project dependencies in our Microsoft Visual Studio applications. We'll look at the problem that occurs when we have dependencies flowing in such a way that the infrastructure and low-level concerns of our application are depended upon by all the other projects in our app. We'll go through an example that shows this particular type of architecture, which is very common, and the problems that arise when one uses it, and then we'll refactor this design, applying the dependency inversion principle at the solution level so that we can improve the design and maintainability of our application. Finally, we'll wrap up with some related fundamentals. In the typical layered or tiered application design, there are separate logical and sometimes physical layers. For instance, it's very common to have a user interface layer, a business logic layer, and a data access layer. Oftentimes, these each correspond to separate projects in Visual Studio. The nice thing about this approach to design is that it supports encapsulation and abstraction. It also works at the application level that is appropriate to each layer. Each level should only know about one level deep, if possible, because this allows for the individual layers to be swapped out at a later date without affecting the layers above it. This provides a good unit of reuse. But the lowest levels are generally the most reusable because there are many more layers above them than, for instance, a user interface layer, which is typically not reusable and usually is at the top of the dependency hierarchy. This diagram shows an example of the traditional or naive layered architecture approach, with the flow of dependencies going from